Okay, so today I will finish discussion of soft limits, and then I also will discuss collinear limits. Soft limits are related to so-called infrared singularities, yes, and collinear limits are related to so-called mass singularities and appear only in theories with massless particles. Okay? Okay, so first let me wrap up my discussion of soft limits. So I told you that when you have when you have a gauge boson or a photon, actually these you can consider not only soft limits of gauge bosons, you can consider soft limits in which has some fermion mass, for example, some fermions become soft and so on and so on, okay? But I'm discussing one specific class, subset of those soft theorems in which you have soft gauge bosons, and then the limit essentially when you have a momentum here k, the limit is k goes to 0. Yes? So now, if we more precisely, then if you take, of course, this is k squared is equal to 0, so the corresponding momentum spinor we can parameterize in terms of the energy of the particle, and okay, this coordinate z, which plays very important role when the whole thing gets is applied in celestial holography. Now, there's one thing which I noticed, that I was sometimes calling square root omega square root of t, sometimes calling square root omega lambda. The reason is that if you look carefully what I was when I was discussing relation between lambda and lambda bar, okay, then I told you that what I found, that in order for momentum to be real kinematics, I found the constraint that this z is equal to z star, the z tilde, which parameterize the square spinor, the conjugate spinor, was the complex conjugate. But there's no argument that the two coefficients in order lambda and lambda bar were the same. The only constraint was that they had two opposite phase because it is the product of them which gives you total energy. So when I'm using like that, the reason now why I can use the same energy for k, this one, and for k square bracket, which is conjugate, is CPT invariance. Okay? So that is something which comes here with real kinematics, and when I really when I make the statement, when a CPT invariance, which means that you have for each, it's related to crossing symmetry, that for each particle we have antiparticle with opposite spin, with opposite helicity. All right. So anyway, so the limit k goes to 0 corresponds to the limit and energy goes to 0, and z can be arbitrary. Okay. All right. And then I considered two examples. One which was just scalar electrodynamics, the simplest possible case, and one which was a little more involved was the case of Young-Mills. And the story is always the same, that when the photon or gluon becomes, when the energy goes to 0, you get a singularity which goes like 1 over omega, leading singularity which goes like 1 over omega, and it factorizes. So in the case which is the simplest case, you have some number of, and when you have this scalar electrodynamics, okay, you have k here, and then, so the statement was that if you compute the amplitude with some number of hard particles, and one photon, in this case, which becomes soft, then this amplitude factorizes in the following way. You have some square root of 2 over a factor, depends on convention. Then you have a 1 over omega, yes, this singular pole, and then there's what I wrote here was a sum over all external charge particles. For each particle, you have this zki. Okay, the difference between z of the photon and z of the charged particle. I assumed actually that these particles, for simplicity, were massless. All right? So actually, sometimes I'll be using z, and sometimes I'm using zk. Depends. Okay? So here I wrote this. It's simpler. It looks nicer if I like it this way. Okay? Times, so this is the soft factor. Okay? And then you have amplitude without the soft photon. All right? That's how it looks like. So I'm summing over all charged particles, yes? And then there's this factor, this pole, essentially, when zk is equal to zi, when the position, when this coordinate z of the photon overlap the position of the external particle. And then there is also this pole 1 over omega, which I'm discussing now. All right? Good. Now, I don't know to what extent Sabina mentioned celestial amplitudes, but the celestial amplitudes are obtained from this type of amplitude, which are momentum space amplitude, by taking Mellin transforms with respect to energies. Yes? Mellin transform with respect to energies, that you perform integration over this, when you take Mellin transform, you take this object and you integrate with the energy to power delta minus 1, where delta later becomes the dimension of the corresponding operator. So when you have such a pole, so such poles, infrared poles, when you see them in celestial amplitudes, are translated into poles a specific number of dimensions. For example, if you have in this case, 1 over omega pole will correspond to the pole at delta equal 1. Yes, because it's the omega divided by omega. So then the poles, the poles which appear at certain number of dimensions of celestial operators contain, when you write this soft theorem in terms of celestial amplitudes, you will have here a pole which appear when the dimension is equal of the operator is equal 1. That will take care of that. And then you have this type of poles on celestial sphere, okay, singularities on celestial sphere. It will correspond, it will essentially represent the fact when you have these two poles, essentially you can think about them as appearing from the operator product expansions of the operator associated to the soft particle and the hard particle. Okay? That's roughly, but I won't, that's not what I'm, the purpose of my lectures will essentially explain where these singularities are coming from. And I told they're coming from because simply when k goes to 0, this propagator goes on shell.
In what way the 0 of the plane, complex plane, is distinguished here? One could think that we can change coordinates and we can have 0 somewhere else, but then...
No, there's a difference. It's always, these are invariant difference. It's always differences which appear. So, yeah. Yeah, so that's why it's always differences. This whole thing is SL2C invariant, so it's always like in CFT, all correlation functions are functions, they depend on the difference of the positions.
ZKI is ZK minus...
Yeah. I already did, sorry about that. In general. Yeah. All right. So this is the leading theorem. The leading soft theorem, which has been known since the beginning of the of QED. Now, what is non-trivial, however, is you can always ask the question whether you can say anything about well, in general, this is leading 1 over omega pole. Okay, whether can we say anything about subleading terms? For example, in this case, like omega to power 0 of order 1. Okay, and it's quite, again, surprising in some way, but yes, you can. Now, This diagram, the leading singularities, come essentially from the diagrams that I told you when you have stuff here, and you have the charge line, and you have the soft one emitted from one of external legs, yes? These all i's, yes, which we're summing over, or possible external legs. Then, okay, well, you have some other particles here, yes? So the 1 over omega comes from here, pole, yes? Now, I also told you that if you look, if you, for example, put this, instead of putting here, you put the photon here, well, when the momentum goes to 0, nothing happens, because you still have the propagator, which is off shell, provided, of course, these are, you know, these particles are hard, okay? So you have that, so, and these, this type of contribution are order 1, yes? Okay, and they appear everywhere. So another, you have terms which are of order of omega to power 0, which comes from diagrams, which I would represent like that, yes? Where just somehow the soft photon is emitted from some internal line, all right? Of course, in addition to that, the terms of order 1, of course, emerge from subleading corrections from here. Yes? All right. This is, to compute subleading corrections coming from here is not so difficult. You will see it in a minute. To compute from them, it looks rather harder to analyze, and that's why this, this whole result, which I'll describe, is called Low's theorem. It's quite non-trivial, but it was, result was obtained by Francis Low at least 50 years ago. Okay, so let me go back to the whole thing. So remember that okay, so let me start from scratch, sort of, and write it here. Like, I'll draw another diagram, which will make, so you have here, there's some photon here, you have another one, you have some charge line, you have another pair, particle and antiparticle, and you have some photon from here, okay? So remember that from this diagram, okay, from that one, okay, we've got that from here, I thought this was very characteristic numerator, which coming from the vertex, which is the product of the polarization vector times the momentum, and this is one times p, and then there was okay, momentum pi. Then there was this factor coming from propagator, and I was telling you there was a sum over the charges, yes, right? And then, okay, with this number of charge particles, and there was and then what I did, and since I had already the pole here, then I said that when this momentum goes to 0, actually the momentum of this particle is just p, yes? That's good in the first approximation because I have a pole here, so this is of order k, yes? So, but if I do it more precisely, I will get this diagram, the momentum, which will go down here to the rest, connect to the rest of the diagram, will be pi plus k, not pi by itself, yes? So that will be that correction with the first source of subleading corrections, yes? All right? So what I get from here is of order 1 over omega. From here, you know, when k is equal to 0, so that, or we know what it is. And then there's a term which will be sum over all charged particles. Now we wait with the charges, and this is soft factor. And now you will have what you have to do, expand. So we'll have a k mu yes, if I take a k mu, then I have to differentiate the amplitude with respect to d p mu, yes? Original. Now this amplitude evaluated actually at k equals 0, yes? This is what it is. This is the correction. And you see k here, so you see this correction will be of order 1. Okay? So I can write it in the following way. I can actually split that in the following way. Okay, this should be d pi, yes? Because I have a charge here, qi. All right? So now I can write in the following way. I can write it pi mu here, and then contract it with this one, yes? Right? Okay? Or I wish I can write it, yeah, okay, I can write it like that, yes? Okay? Well, I prefer to do it like that. All right? So this is so this is correction. This is correction which coming from just expanding, taking into account kinematics more precisely. And this will give you correction of order 1. Yes? Now, well, that's good. But there is a slight problem. If this were the entire, of course, we know it's not entire, the subleading correction, but okay, we can ask whether this makes sense, having just correction coming from here and nothing from here. It doesn't make sense because you see that this is not gauge invariant. When I set the polarization vector of replace the polarization vector by the momentum, then this gauge invariant object should vanish. Yes, it doesn't. There's no reason why it should vanish. In this case, the charge conservation, which I told you that sum over qi is equal to 0, doesn't help at all. Okay, I used that one, charge conservation, to prove that the leading correction was gauge invariant before. Okay, so now the only way you can make this when you invariant with multiply by k nu here replacing, is to have something which will be antisymmetric and mu and nu indices. Okay, so I can make each kind of invariant by taking this and subtracting okay, and so that will be gauge invariant. It makes sense. This is coming from here, and then actually what the Low's theorem was to show that this term appears from the diagrams in which this photon is emitted from internal lines, and you can show there is nothing else. Okay, so that is Low's theorem, and essentially it tells you that the terms of order 1 are coming from here. Okay. Okay. So now, so this is this. By the way, this object is clear what it is. Yes. This is acting. Let's consider amplitude in which you have just everything is scalars. Yes. Well, scalars, and you have just one additional photon. Yes. So this object is acting only on scalars. Yes. And you see what it is. Yes. In momentum space is clearly the angular momentum operator. Okay, and there's no spin part because these guys have spin 0. Okay, the scalars. So this thing here is essentially angular momentum operator up to a sign j mu nu and some factor j mu nu. All right. So Low's theorem is telling you that I can write now fully that the amplitude in which you have the soft photon, okay, is up to the order 1. That's the leading term, and minus I k nu j I, is I mu acting on the amplitude without the photon. Okay, so P1 to Pn. Okay? It's a very nice and compact formula. Okay? And again, there's a similar theorem which holds for Yang-Mills theory. The rule is, as you remember, that well, it's a little bit. There's no like overall factor in Yang-Mills theory, but instead of charges, you have structure constants. This times, of course, the coupling constant, Yang-Mills. Yes, and there is a similar relation, similar theorem, subleading theorem for Yang-Mills theory. But it is, okay, nobody cared about it. It was only derived by Casali, like, I don't know, like 10 years, like just one whole thing in the context of, when considering celestial, when celestial holography became, because sort of focused on those sub-theorems, right? But it's always this angular momentum operator which appears. So now we may ask, now how does it look like, the soft theorem, how does it look again in these, okay, celestial coordinates, yes? Or the spinorial notation, yes? All right. So now, for that, of course, now momentum, is always, I told you, momentum was roughly, yes, up to, in the matrix notation, it was lambda bar, yes? So instead of a differential, when I have a function of the momenta, after I trade them into the helicity, into the momentum spinors, then, of course, the derivatives with respect to the momentum will become essentially you can trade them into derivatives with respect to the momentum spinors, yes? And this is really a trivial exercise to show that if I consider the angular momentum operator, which is, I told you before, it was Pi for each particle, okay, that can be written as a derivatives with respect to lambda and lambda bar, yes? And so the price formation you take, of course, you will get sigma mu, sigma bar mu, alpha beta. That is, I think that could have appeared already before in Tim's lectures. This is the combination, anti-symmetric combination of sigma and sigma bar. It's actually this is symmetric and this is alpha beta. It's usually called sigma mu nu. Okay? And then it is a derivative with respect to lambdas. Now contracted with that. Yeah, of course, this one, these guys have to be down. Okay, so yeah, this one is down, and then okay, that's fine. And then there will be plus sigma bar mu, sigma nu. Since you are starting now with sigma bar, that will have dotted indices and with symmetric in those two indices, and there will be lambda bar alpha dot. Okay, d lambda bar I. Okay? So this is the first step. You see that now, once I go to Hellyst amplitudes, momenta are gone. Okay? And then this is, now I'm replacing all momenta by, then essentially in this case, we have one photon. You can repeat the same discussion, you have more photons, but essentially there are no more Hellysts, there's no momentum spinors. The only thing which was coming which I have here, is the photon, it disappears, so just pure scalar amplitude, yes? So essentially, the only momentum of the scalar amplitude depends on the momentum only, yes? So I replace them by lambda, lambda bar, and then the angular momentum operator becomes, this is what you see. Oh boy. Huh?
In the second pair of sigmas.
There's, of course, there is this. And anything more? Okay, good. Yeah. Okay. So now, this alpha dot, this contracted here, and this contracted, they have to go like that, yes? Beta dot here, of course, yes. All right? Yeah.
So the leading soft theorem is supposed to be correct to all loop orders, right? Is this also supposed to be protected to loop orders, the subleading soft theorem?
What do you say?
Is the subleading soft theorem also supposed to hold at loop orders, or does it get corrections in general?
Oh, okay, you're asking about sub-subleading. Okay, sub-subleading.
No, just the subleading. Because the argument you gave, at least the picture you drew, is tree level. So
Yes.
does this get corrections from loops? The leading is not.
Subleading, yeah. Subleading, I'm not sure.
Okay.
Yeah. But also a related thing is that is about, in QED that question could be answered, I'm sure. Okay, but you're asking also another thing. What about sub-subleading, which means omega to power omega? Okay, yeah, of course. This is you can do that, and you can go then. Actually, there is no any pattern of the type of factorization. Or factorization with a factor or some operator acting on the amplitude. So usually people say it's not universal.
You can't fix it by the same demanding gauge invariance type of argument.
No, that's the whole point. So that here essentially it's fixed by it's not only it's fixed by gauge invariance, but you have to prove there is nothing left over. Actually, there's a nice paper about in my notes there is this notes which general notes about amplitudes, but also there is a lecture. There's a lecture which lecture notes from slides from some, I think it was in Princeton, and you see here there's a reference list. And one of those references is a paper by, I think, Byrne and Nola and so on, which we give a very nice discussion of that, proving that there's nothing left and so on and so on. Okay? But that's again, it's at tree level.
Okay.
All right. Okay. So now, okay, so the question is now, so we are, no, but it's not. This would be good if you are like into Helist amplitudes, but we are here into celestial holograph, yes? So I have to do one more step, which means to translate those this angular moment to operate. Now express everything in terms of Z's, yes? All spinors now, trade them into ZZ stars and omega and omega tilde, actually only omega, and into energies, yes? And then, so then I have to still change variables, and instead of differentiating with respect to lambdas, I will have to respect to z's and so on. I differentiate with respect to energies and so on and so on. Okay, and that was again surprisingly right. That was I don't know if Tim is here, but it was done again a few years ago. Not long ago. It's a very simple exercise of we see differentiation. Yes, so we can show that that actually. That this particular combination here, let's choose specifically positive helicity soft photon or gauge boson. In this case, it doesn't matter. Okay, K nu, J mu nu, I. Now, essentially, by changing to those all momenta. Integrating them in terms of coordinates, celestial coordinates of the Z, projective coordinates of momentum spinors, that becomes simply, well, from here we get 1 power of the, you will get 1 power of the energy, and there we have, now I'm using Z bar or Z for the photon should be Z and of course there is derivative with respect to energies. It's because it's one part of it. Okay?
Second one is unbar.
These are bars, of course, they're always bars. Always bars are bars, yes. Yeah. This for a positive helicity, for positive helicity photon. So then what I get, that this can be written as simply, all I get at the end, this is one of the leading term, which is, I write it before, Qi. And now I write it like explicitly Z minus Zi, yes? Plus, now I will have also, okay, from here I will have Qi, I can factor out Z minus Zi, I think. And then there will be this operator here, Z bar minus Zi, Zi bar I plus omega I, d omega I. All right. Okay. So now, so this is what you get. And this is of order 1. So now, if you do this on celestial amplitudes, yes, this term will have a pole which appears at the dimension operator of when delta in the Mellin transform become 1, yes? This one will be, this one has no power of omega, so it will become, this will become a singularity at delta equals 0, yes? And now, and the coefficient, what you get here, well, also when you do Mellin transform, you have to take care of the, okay, the whole, everything you Mellin transform, including that term participates in Mellin transform, but it's sort of trivial because derivatives of, with respect to omega, they multiply by dimensions, yes, because you have omega to power delta, yes, and omega just adds dimensions, yes. So transform, this term is translated to some simple functions of the dimensions of operators. And what you left here now, essentially this thing, well, with that or with that, okay, Z minus Z bar, I pointed out before, yes? So that whole thing now becomes something more interesting, yes? The subleading theorem becomes more interesting. It looks something which looks more like these word identities that Piotr was describing for Henchman tensor and so on and so on, okay? And that, again, then they have in celestial holography, then you find some interpretation of, you find these subleading soft singularities can correspond to certain identities and certain properties of celestial conformal operators. Second line? Oh, that one? Oh, that came from here.
Yes. He's asking about the Q over Z minus Zi, and that just comes from the denominator.
Oh, yeah, yes, sorry. You remember it was here. Yeah. So that it came. Yeah. It has to be Z. Let me check. Yeah. What one?
No, because there is an equal sign. I assume that you go from the first line to the second.
Oh. No. It's all right. I'm used to working on a small blackboard, 2 small blackboards. So yeah.
In the second line, is it Q or Qi?
Q in the second line, of course, because you have a sum. So sum over. I should write if I write it like that. I should sum over I. Yes, explicit. Yeah. We can put bracket. I put here. Yeah. All right. Acting now. I have to put here with bracket on the amplitude, yes? All right? Still? The prefactor is just identity. That is a separate that's identity for the energy. This is.
The one outside the brackets.
Hmm?
The one outside the brackets. The typo. The z bar minus z bar I.
Let me check. Let me check. It should be. You say it should be z bar. Yeah, because z. You are right. Because from here, yes, that's true. This guy is this guy times complex conjugate. Yes. So it has a bars, and I cancel. So from this. This bar, if I multiply now, if I divide it by that factor, will have a z minus zi times z minus zi bar. Yes? And then this will cancel this, and I have that, so it's correct. Okay? All right. So this is the celestial, this is the soft theorem written now in terms of those projective variables. Okay, and this is the way I derive. There are many ways of deriving, but here, to do that, I simply what I did, I just replaced derivatives with respect to a lambda. I just change variables from the momentum spinors to these projective variables. Yes. Okay. So we see that this is of order 1, leading is of order 1, and then the sub-leading is non-universal, which means you cannot make a good, interesting statement about it. Yes? It depends on the process and so on and so on.
Do we say that this is universal?
Huh?
Up to subleading, do we say that this is universal?
Yes, because it's a what do you mean subleading?
This one. Subleading is theorem. Do we say that this is universal?
I would say,
Because
what do you mean?
There are some higher dimension operators, some dimension 5 operators that you can put in your effective action, which actually give some corrections to this. There's a small.
But what do you mean? In pure QED?
In QED, this is true.
Yeah, exactly. That's what I'm saying.
But it's not
What?
universal in all theories with like a U1 here.
Oh, no. Well, for me, QED is quite universal. I just, if you want to talk about extension, going beyond the standard, but that's you do it on your own. Okay?
what do we mean when we say it's universal? Do we mean that it's the same for other theories?
No, here it has a different form. For example, you go to Young-Mills, then it has a different form, yes, in the sense there's a similar. Actually, in Young-Mills, again, there's a leading is universal, subleading is universal. Now, what is very interesting about gravity is that, to discuss gravity, I won't do it here, but gravity is not difficult to discuss because although if you try to compute diagrams in gravity, okay, now in Young-Mills theory, it depends how you count, there are 6 terms, yes, you know, momenta and so on, okay? And gravity there are more than 100 terms, so good luck if you want to compute this type of a diagram which graviton splits into 2, okay? Fortunately, already for like 30 years, it is known that gravity in some ways is squares of Young-Mills theory, at least at the level of 3-level scattering amplitudes. Okay, what happens is that to compute, for example, this process, you get this 3 graviton scattering. Or what you have to do, well, we have a vertex, yes, and you have in principle, you have a vertex and the wave function and the wave functions. The wave functions actually of spin 1, of spin 2, which is for graviton, plus can be simply construct a symmetric product of, you write epsilon. Okay, I need that. Okay, a symmetric, of course, symmetric combination. That, of course, it's an automatic trace. So a symmetric and traceless combination of that is just you can write as a product of 2 polarizations vectors. That's one thing. And then actually what you can show, and this was already known, and this is a very interesting result, which comes from string theory, essentially KL by Kawai, Lowell, and Tai, that amplitudes in which you have some number of gravitons can be written, as I mentioned before, as amplitude in which you have just the gluons with stripped color factors, yes? Okay, these are called partial amplitudes. And multiply by some sum of the type, where you have some factor, and you simply multiply all plus here. Okay, for each graviton, you have a plus here, you have a plus here, and so on and so on. And then it's a specific combination, you get that. And then these amplitudes are becoming tractable. And what you can show, that
This statement about tree level, or you can...
no, tree level is known. For beyond the tree level, it's actually being investigated now. Okay. I don't know by whom, but essentially it's not easy to prove it beyond at one loop. Okay, it can hold, but it's not obvious, I think. Yeah, there's the whole thing whether this goes now these days is named double copy, yes. But actually the basic ingredient is that the polarization, you can just factorize this graviton scattering amplitude. It's like that, and then in addition, so that's one thing that you can see, you can write them as such combinations. But there's another progress coming from another place, from twistor theory, which you can find really a simple expressions for many gravitational amplitude. That it was the work by using twistors, and there's a classic work of Andrew Hodges who did this type of things, which generalize so-called MHV formulas to gravity. Okay. Now, the next thing I want to discuss the collinear limits, but before, I just want you, I already warned you that I'm interested that this is what is the physical meaning of those infrared singularities. Yes, one way you are like, as Yannick pointed out before, okay, it somehow tells you that S matrix is ill-defined and QED, but still, we use QED, and QED is actually, QED is actually one of the most accurate theories constructed by humans, which agrees with experimental data, I think, at least to 10 significant figures, yes? So S matrix must exist, okay? Or I think we are doing something right, all right? So now, how physicists deal with those singularities? I mentioned before, that when you have a soft particle, yes? Well, you have here this problem appears with omega goes to 0, yes? Energy goes to 0. With a soft particle, I mean, there's no way that you can construct a detector, yes? That would detect photon which have absolutely 0 energy. There's always some error, there's always some energy resolution, okay? So in other words, when you compute cross-sections, which is taking a squares of them, when you do cross-sections, you square the amplitudes, and so the cross-section, for example, you have to take the square of the amplitude, and then this cross-section for particles going into certain range of phase space, it is usually called Lorentz invariant phase space, okay? So in our case, when this is, has a soft photon and some other particles, it is so that is essentially soft factor, and let me divide by omega, yes, because that I will factor out explicitly 1 omega pole, that's square, times the square of the amplitude, now, which is pure scalar amplitudes, times now I want to integrate the photon, yes? The photon phase space, which is, this d3p divided 2e, and these coordinates is is that you have to integrate over Z, and you integrate over all energies with 1 power of energy, yes? Okay? And you multiply, and then, of course, what you have here, this phase invariant phase space without the photon, I call it X, yes? All right? So you see here that when I compute the cross-sectional probability of finding a photon, I have from here I get 1 power omega, and from here 1 over omega square. So d omega omega, and this is infinite singularity, which I integrate to 0. But now what I have to do, when I'm computing cross-sections for photons, I have to integrate only over the range of energies which are detectable, yes? So I impose a cutoff. That will produce a result which is logarithmic in the cutoff, yes? But then, so for example, from here, I produce like a log of this infrared cutoff. All right? All right? So I have infinite cross-section. That means that makes no sense, yes? Okay, because you get you have this is a leading order, yes, for producing for electron scattering, and then you have this correction will give you infinite corrections. That makes no sense. So the point is that adding to that, what you have to do, you have to diagrams in which you do not see photon, yes? Okay, so for example, with loops which have like that. And again, squared, yes, in probability. And what happens is quite interesting. It's a so-called Bloch-Nortzig theorem, which is rigorously proven by Bloch-Nortzig already in the 60s, that these logarithms cancel and you get final answers which depend essentially, well, you have some function, we have a cross-section for example, electron scattering with a photon which is energy smaller than your resolution energy. Okay, and this will be finite. It will be logarithmic with this resolution energy, but it won't be infinite. All right? Okay, so this is what is. So physically, now there is one thing which I also to make point here, that because I was asked this question before. All these, you see, what I did here, I was using Feynman diagrams, yes. So I could be any number of dimensions. I never used actually the number of dimensions here, yes. So all these soft theorems hold also a high number of dimensions, if you want to consider them, okay? But when you do this, there's a phase space. This is what usually, you took d3k by 2 energy, yes, the phase space factor. And then when you have if you have a higher number of dimensions, you have this is higher power of omega, so there is no singularity. So these infrared singularities appear only in dimensions 4 and lower. And in dimensions lower than 4, they are more violent. Yes. And 4 dimensions are very, very special. It's just logarithmic infrared singularities and logarithmic ultraviolet singularities, at least in our normalizable theories. Okay, good.
But what is mu in diagram where is no soft photon?
No photon.
Yeah, but what is mu?
What is what? Mu is infrared cutoff.
But what is
Oh, here, yeah, that if you go with you here, you will have to introduce a cutoff because you have integrals of the form d4k divided by k to the 4th. Well, now, and k goes to 0. It's infrared, so that is infrared cutoff. Here it is energy resolution, and then they are, when you choose them appropriately, then they cancel. Yeah. Well, yeah, they will cancel.
Okay, so it doesn't vanish, but it regularizes, right? So we still get a correction from soft.
Oh, yeah, okay. Then the next step, of course, then I have a logarithm, yes? And if I take this small logarithmic, if I take these logarithms, yes, still it's big, because I take a small resolution, I have a log of a small number. Okay, so now what you have to do, you have to have some perturbation theory, okay? And then you get something sensible, and at the end of it, it's very nicely described by a classic book by Peskin Schroeder on quantum field theory. What you find that the probability for electrons, let's say, scattering without a photon is 0, with 1 photon is 0, and the number of photons 0. So it means that the electron is always surrounded, is dressed by a cloud of photons. And that's what it is. Yeah. I know this argument about having detectors and having resolution, it sounds maybe a little bit anthropic, yes?
Just why the same cutoff in loop as in physical?
Yeah.
Because this kind of sounds a little.
Well, no, but then you for example, yeah. So you say you have that's true. The correct is this resolution has to appear here, yeah. Okay, okay. So that is essentially. So what I'm saying that although the whole story holds in a number of dimensions, the fact that you have really this, for example, the 5 dimensions, you have the probability for electron scattering with one photon is finite. Okay, but not in 4. It's 0. But for essential holography, it's not something that that plays a role, because actually we consider amplitudes. We usually don't think amplitude squares, but there are more and more people now who think more about who pay attention to, who consider the squares of amplitudes and their properties. Okay, I think that they become I think this subject will develop further, much further. Okay, so now what about collinear singularities? I told you, okay, so what about collinear singularities? That's something which is, appears. So again, let's have some charged particle which is emitting a photon. Okay, the momentum has a p. This again is a momentum k. So I will now write it. K has some energy and some free momentum. So I can write omega times just some where k. Of course, I can write this omega, the magnitude. This is photon, so k squared is equal to 0. So you write this omega times, it has length omega times some direction vector, and then p has again some energy omega p and momentum p. And then now the on-shell condition tells you that p is square root of the energy square minus m square times the direction of this momentum. Yes? Okay. So now I told you before that this numerator coming from the propagator is 1 over 2 p dot k, yes? A massive Theorem knot. So this the kp on the other hand is omega. You the scalar product. Again, in my signature, times cosine theta. Well, theta is the direction between the two particles, yes? The angle. So now you see that the only way to make it 0, as it is, to make omega 0, because this cannot be 0, yes? Because this is different from that. But now there is a special case if this particle has a mass equal to 0, or in the case we have two particles which are massless. What is happening here that you get, in the case of mass equals 0, you get omega times omega p times 1 minus cosine theta, where theta is again the angle between the two three momenta. Now we see the following thing, that when the two particles are moving in the same direction, this blows up. So there's another way of jumping on the pole of the propagator, which is possible only in massless theory, in which the two particles move in the same direction. And then the singularity appears when the two particles are moving in parallel directions, in the same direction. Okay? So now, okay. All right, oh, by the way, and what I will do now, I will show example how this can be computed, for example, in Young-Mills, how this can be, this will to some singularity and of that type when we compute Feynman diagrams. But the best way, another way of seeing, which is actually very more enlightening, and it makes it makes a direct connection with celestial holograph, is to write this cape. You see this dot product here. Before, actually, I'd write twice, yes? It was omega, which is omega of energy, times the product of two energies, assuming, again, the two are massless, yes? Times, I told you, z, which is z is this momentum, this projective variable of the photon, minus z p square, yes? Okay? And I told you before that this can be 0 if omega goes to 0, but now you have another possibility that actually the two particles move in the same direction, and this corresponds to z's of the two spinor of the two momentum variables being the same. So it is essentially, when you do in terms of celestial amplitude, this corresponds when the operator associated them coincide, yes? Okay, so that now you expect some poles. If you think about celestial conformal theory, you will that will be related actually to what Piotr discussed, to operator product expansion of celestial operators. Okay? Soft theorems correspond to word identities, celestial conformal field theory. The collinear limits, by using collinear limits, you can extract operator product expansion of the celestial operators associated with elemental particles, with particles. All right, so now, okay, I will just tell you how to I will finish just by quickly tell you how to parameter, how to talk about it in terms of the momentum spinors. So what you do, you have a moment, we have a k, okay, and I told you it is now we have two particles, yes. So it's better to give them the same names like PM and PN, yes. And I'm saying that the two particles now are the two momenta are parallel, the three momenta are parallel. So I can write, so I would write n is square root of omega n times, again, I have this Zn1, okay? And then m is the same thing, yes, square root of omega m times Zm1. And now, essentially, I'm telling the point is that in the collinear limit, they coincide, yes? All right? So now, the way to, so what it becomes, in that limit, both become this Z1 times, so it becomes essentially the two particles, they merge sort of to one particle, yes, with momentum which is the sum of the momenta, yes? So I will call omega is equal to omega m plus omega n. So at the result, you will have the two particles here replaced by one particle, yes? And essentially, instead of two particles, you have one particle with momentum p, which has the same projective coordinates, but here it will have the square root of omega, yes? So you see that all three, okay, you can write now that the mth momentum spinor is some factor, which is the ratio of those two, yes, times this, and the same thing for the other one, all right? So at the end, what you get, and I will write the result for just as example of such a collinear theorem. So you see how it looks like. Yeah. So if you have for gluons, okay, which are generalized, you have an amplitude in which you have two guys, PM, and now with color index n, and some Helist. Let me just write this Helist, this collinear theorem, and both have a plus, Helist plus. Yes? So we have this one will have and this will have a PM, Pn, An, and plus. And now what I'm doing is consider collinear limit in which I described before, that essentially that momentum P is parallel to m, essentially is some fraction of this total momentum P. Okay, which I told you carried by two of them. So we can show that this is like this amplitude is like the amplitude in which you replace these two guys by one gluon with momentum P. For plus plus, then this gluon will have same polarization. If they are opposite, there are two options, there are two possibilities. It may be this gluon, which appears here. If this plus minus, this can be minus or plus. Okay? And then the color index. Now, you see that all of these three guys are connected by the vertex, yes, in order to produce the single, to get on this pole. And what you get here, some index A, yes, and then you have, of course, now the structure content that links all of them, A, N, A, M. Of course, I should be careful here. I should multiply also by the coupling constant, which comes from here, yes. And then what I will have here is, so this amplitude. And now the factor which will appear is here with the total energy omega divided by the omega n, omega m. There will be a factor like that, which comes simply from those, yes, from here. And then you see that in this case, again, you have really singularity, this collinear singularity manifest as a pole Zn minus Zm or Znm. So you have a pole. Yes? Okay, so now if you do, so this is what you get, and you got similar statements which you can prove simply by, okay, this is all in my notes, okay, so you can, in this physics reports plus the notes from Princeton. And so you see that this collinear theorem gives you a pole, you get the poles when these spin-orbital projective coordinates coincide, yes? So it's indeed like you have these two operators. Now the positions of in celestial holography, you have these two operators which merge to one point, yes? And you replace this operator representing the two positive Helist gluons, yes? Okay, by a single operator. So it's exactly OP. And the OP of two gluons with the same Helist has a pole, simple pole. So it's like the simplest possible OP that you can think about. Okay? But it is, that is how it looks like. Now, I cannot, you can ask, what about subleading? What about, there will be also poles, yes, and the subleading terms, which are of order Z to power, they won't have a power 1, of order 1, yes? That's interesting that, there is no, there's a theorem, which I would call half of subleading theorem, and which, actually, this is the work which I did, I don't know, many years ago with Stieberger, which tell you that the subleading terms, subleading collinear terms in Young-Mills scattering amplitude are related to gravitation amplitudes in which the two collinear guys are replaced by a gluon. In which two collinear gluons are replaced by a graviton. So you get a surprising relation between subleading terms in Young-Mills theory and and the scattering amplitudes involving gravitons. Simply what you do, you replace the two parallel gluons by a graviton which is moving in the same direction and essentially inheriting all momentum. Okay? Again, the statement is about partial amplitudes, yes, because again, I have to get rid of the color factors. Okay? But this is it's half because it doesn't allow completely expressing partial Young-Mills amplitudes, the sublinear terms, in terms of gravitation amplitudes. You get half of relations, which would, you get only half a relation that you would need in order to express collinear Young-Mills amplitudes by gravitation amplitudes. So that's the first statement. The second statement is also interesting, which you say, well, okay, so now we have, now we compute cross-section, yes, and you have two gluons, yes. It's infinite, because you will integrate over D2Zs, yes, and then you hit the pole. So again, in the cross-section, when you integrate over all gluons, the phase space include that configuration in which there are two moving in the same direction, yes? All right, okay, so what do you do next? Who has a guess? How to get rid of that problem? You get there again infinite cross-section, yes? Huh? Exactly. So here we go with detectors. Yeah, blame detectors, yes? Okay, you say that, well, there is no way to pick two exact. Actually, that problem doesn't appear in QED, yes, because you cannot have you have always one electrons which are massive, and you have a photon, and for that you need a non-abelian theory. But still, when you talk about people compute jet cross sections, yes, in which they take like two gluons, integrate over all possible directions, and of course they hit singularity here. So the only way to do is exactly. So you say that, well, there's an infinite angular resolution, yes. You cannot measure angle between two gluons, okay, to arbitrary precision. You have add these diagrams with other, you have add these diagrams, these tree-level, for example, tree-level including tree-level amplitudes involving gluons, with amplitudes involving smaller number of gluons, because you can, okay, two gluons without these two, to the amplitudes which should be one gluon instead of two. But you cannot tell a difference. And then singularities cancel. And this theorem is called Kinoshita-Lee-Naumburg theorem. It was never really, I don't think that was never rigorously proven. But it is, people believe in it. No, loop correction, no. For loops, you have, I think Kinoshita-Lee-Naumburg, of course, you block Nordzig actually can prove to all orders of perturbation theory, no problem. But then in Young-Mills, yeah, Kinoshita. Yeah, you have to prove, you have to go to, if you go to higher number of loops, of course, then you have, of course, that should go to whole, because now you have two parallel guys, now you do loop corrections, you have spin singularities, so the whole process goes on and on and on. And, but still, people at hadron colliders are happy, and they measure cross sections, and they are finite, yes? So it must work, one way or another.
Would it be maybe naive, but would it be more honest to say that we treat it like effective field theory, that we basically impose higher cutoff, and would it be possible to have like additional degrees of freedom where we reach very low energies or something like this?
Well, okay, fine. Okay, you can do that, but I'm saying that it's again, since this is QCD, it's not QED, okay, and QCD again, the QCD agrees with experimental data to rather high precision. I cannot tell you, like at least 5 significant figures. I mean, at least like 3 loops or 4 loops agree, and they involve this type of computations. When they do, also what you can do, you can also define some variables which are infrared safe or parallel safe, and there are such variables already exist for many years, I know, and they're usually called like thrust, and there are other variables which we compute explicitly, but at the level of probabilities. So probabilities you can make finite, and you can make a sense out of, you can make the higher order partition can be small, provided that you use a property normalization scheme and perform appropriate summation. But this is, yeah. All right.
What if the particles have opposite helicity?
What if?
What if the particles have opposite helicity?
Oh, yeah. For opposite helicity, that this has to be plus or minus. So, for example, there is a term, and there are poles which is Z1 over Z, and poles Z bars. Okay, so for example, if you want to have, I'll give you one example. If this is plus, this is minus, this was plus, yes, this is minus. Then there will be a term like that, which will have omega, this will change. So it will be omega n divided by omega m, divided by omega n times this total energy. And there will be pole, which will like that, yes? And this will multiply the plus, but then there will be term in which this amplitude, in which the combined, then we'll have helicity minus again. And then the factor here would be omega n divided by omega m omega. But now that there will be anti-holomorphic pole, Z bar m minus Z bar n. Okay? This all, yeah. This is all in those lecture notes which are posted. I mean the link which are linked as my literature. Okay. In other words, these are poles which go like 1 over, in other words, in this notation, if you go back to notation which I had used before, which we used for momentum spinors, these were angle products, yes? And these were square products. Okay? More questions? All right, good. Okay. We have a break or not? We have some short break. Yeah, again, 15 minutes. Dobra.
May I corner you again about something that'll definitely be difficult?
Yes.
But,
Okay. Like before crossing. Okay. So
this